Well, we're back. My name's Eric. We're continuing to talk about all things power, bases, exponents, negative exponents, fractional exponents, properties of power. And my students right now are doing a little review. I called it Topic 8. And I'm going to work through this review for their benefit because our schools are shut down right now. But if you're out there on the web and you come across this and you get something out of it, hey, that's great. Glad to help you out. If you have questions or comments, I'll do my best to respond to all of them. Let's get started. In the previous video, which I hope you watch, it's in the playlist, we had a discussion about what a zero power means. Any number to the zero power, with one exception though. Otherwise, any number to the zero power makes 1. So the answer to this problem is 1. And it's not because of -7. I could have asked you what's 5 to the 0. The answer would have been 1. In the previous video, you saw 2 to the 0 is 1. So once you get used to this idea, it's actually a pretty easy problem. Zero power of basically any number except 0 itself makes 1 for an answer. Next problem asks us to write 5 to the -4th, evaluate it, write your answer as a fraction in simplest form. Okay, well, previously we learned what a -4 power does. 5 to the -4th is the same thing as 1 over 5 to the 4th. It's not a negative answer, it's just a very, very small answer that's just barely bigger than 0. Now, you may want to use a calculator for this to figure out what 5 to the 4th is. I know it's 625 because I do this for a living, but feel free to plug that into your calculator or your phone to determine that that's 625. That's correct. Now we have a -5 power of -2. What does that mean? Well, it quite literally means 1 over -2 to the 5th power. A calculator might help you get this right. If you're trying to do it without a calculator, I can show you how to do that. You write down 5 factors of -2, and you just start pairing them up, kind of like an upside down factor tree. -2 times -2 is +4. -2 times -2 is +4. Don't forget to bring this one down. Now you might want to start on this end. 4 times -2 is -8. And you still have this 4 that has to come down. So what's 4 times -8? It's -32. So it's okay to write the answer like this. I think most people would prefer to see you put that negative here or here. My favorite place is to put it up here with a 1. So I'm going to write -1 over 32, circle it, and move on. Hopefully you can still see problem 4 in the picture here. I'm going to assume you can, and we're going to get this one done before I move the paper. Problem 4, simplify this and don't use any negative. Use only positive exponents. So right here there's a -3 power. They don't want to see that. Well, one of the first things you can do is you have to make an assumption. Assume x is not 0. Okay? Then x to the 0 power is just 1. And what's 9 times 1? 9. Well, does that mean there's no x's here? Yeah, that's what that means. So really what you're trying to do is simplify this. And we've had some discussion about what a -3rd power does. It sends all 3 y factors under a fraction bar. But that 9 doesn't go down with it. It stays upstairs. All right. And so far, we haven't really had to add anything to our list from the previous video, property-wise. We can handle negative exponents. We haven't had any fractional exponents yet, but I assume they're coming. So, all right, I'm going to scroll this up. We're going to work on problem 5 next. Try to keep a good pace. Feel free to pause the video if there's something you're not sure about, rewind it, and so forth. Problem 5. Simplify it, write your answer, use only positive exponents. So, okay, there's a couple things I can do. What's 10 to the 0 power going to make? That's going to make 1. I see r to the negative 11th power. Makes me think those r's would like to be down under a fraction bar, like this. Well, down under this fraction bar already is 3 squared. That doesn't mean 3 times 2. It's not 6. It means 3 times 3. So out of this, you get 9. And then there's an s that seemed content to stay up there. Well, I'd be thrilled if my student came up with that answer. That's a good answer. This is also a good answer, though. S over 9r to the 11th power. Put a box around it so your teacher can find it. That's a courtesy. I think he or she deserves. Okay, I'm going to give you 2 ways to do this problem, and they're both pretty good. One way is better, but I think these are both good ways to go. Problem 6, ready? On the one hand, you can think of this as being 1 over 4 to the 5th power. Then you can divide 4 to the 5th by 1, if you want. And then you can multiply these two and these two, and you end up getting 4 to the 5th over 4 to the 5th. Now, if you really want to know what 4 to the 5th is, look it up on a calculator. It turns out to be 1,024. You don't really need to do that, though, because you know that a number divided by the same number, you don't really have to know its value. The answer is going to equal 1. And that's the answer to this entire problem. And that's a good way to do this problem. I'll show you a better way. Here's a better way to do it, okay? Let me erase this. There's a property about multiplying 2 powers that have the same base. Now, it's got to have multiply, and you got to have the same base. But when you have that, it comes up quite a bit. The answer ends up being just a to the j plus k power. You can write a product of powers as a single power. Just add the exponents. But it's got to be multiplied, and you have to have the same base. Okay, so there's the rules that have to be followed. But that's what I have here. Both these powers have a base of 4. There is multiply here. Make sure you have that. So what I would have done with this is written this as a single power, where you go negative 5 plus 5. Negative 5 plus 5 is 0. And by now, I think we're used to the idea that any non-zero number raised to a 0 power has an answer of 1. And that's exactly what we got when we did it the other way. I like this way a lot better. Okay, I can see that we're going to need to add to our list a little bit over here. On the right, and some of these come from the previous video. These two in particular were explained in the previous video. There's something called the power of the power. You have a to the j, that power, raised to some k power. And the answer is a raised to the j times k. A raised to the jk power. And no, I'm not kidding. How does that apply to this problem? Well, that's what I have. In this problem, the base is p. Well, that's the a over there. You have 6 as an exponent on p. That's like the j. And then that whole structure is raised to a 4th power, as in like to a kth power. Well, what's the answer? P to the 6th raised to the 4th is the same as p to the 6 times 4 power. 6 times 4 is 24. So what they want you to squeeze in this tiny little box is p to the 24. This problem works pretty similarly. You're just going to take the negative 5 exponent and the 3 exponent and multiply them together and get the negative 15th power. Now, they don't want you to stop there, though, because apparently the person who wrote this problem doesn't like negative exponents. Or at the very least, they want you to get used to the idea that a power with a negative exponent can be written as 1 over that same power, but with a positive exponent, as per this rule right here. Oh, we're out of room. We're going to have to scroll again. Scroll and erase. We're on problem 9 now. And then we'll scroll again and get down to the second page. Write your answer using only positive exponents. Okay, we'll do that. Well, first of all, I know how to handle this. I can handle the numerator with this property right here. So what I'm going to do is keep z to the 5th on the bottom. And up here I'm just going to write z to the 8 plus 2 power. But z to the 8 plus 2 is z to the 10th. Now, of course, we know this symbol means divide. But there's a rule very, very similar to this, which says instead of multiplying 2 powers with the same base, if you are dividing 2 powers with the same base, all you have to do is subtract the exponents. It has to do with cancellation. In other words, there's a lot of z's up here and there's a lot of z's down here. But any z on the bottom divides away one of the z's on the top, so that in the end, it looks like subtraction. And that's what you do with the exponents. You subtract them. So the answer to this is whatever 10 minus 5 is, and that's z to the 5th. Answer. Okay? Next page. Hopefully that's still in the picture. I better check to be sure here. Hold on. Oh yeah, it looks good. Okay. Write your answer using only positive exponents. Well, are you tired of getting new properties? Because so far we have, 1, 2, 3, 4, 5, 6 properties. These are written on the same line. Well, we need a new property. I'm sorry. I know, it's probably driving me crazy. What would be a combination of these two? This one says powers with negative exponents really would like to see those factors below the fraction. And this one says, yeah, but if they're already below a fraction bar, they would really like to be back up on the top. Okay, well, think of this, though, as being 6 to the negative 2. Those 6's wish they were under or dividing. And these guys also have a negative 2 power. So if you're looking for a property here, the property would go something like this. A over b to the negative k power is equal to b to the k power over a to the k power. Like that. So what I'd do with this is I'd write equals n squared up here and 6 squared down there. You could put a box around it and call it done, or you can call it n squared over 36. Okay, we are doing a power of a power for the most part. If they didn't put this 3 in here, all I'd have to do is go s to the 8th to the negative 5 and just lean on this property and multiply the 8 and the negative 5. But I have a power of a product. So here's what you're going to want to do. First, remember, negative 5 power means 1 over whatever it was in there to the positive 5 power. Second, you're going to want to put a little 1 on here and try to, and this works as long as you have multiplication. And you're going to want to try to think of this as 2 separate problems. What would you do with that? Well, you do 8 times 5. Okay? 8 times 5 is 40. What would you do with that? Well, you do 1 times 5. 1 times 5 is 5. Now, there's a tendency for people to write 15 here, but that's not really what it is. It really means 3 times 3 times 3 times 3 times. One of those things you should probably do on your calculator. I think the answer, though, is 243. So you got 1 over 243 s to the 40th. I wouldn't be mad at you if you left this as 3 to the 5th power, though. I really wouldn't. Problem 12. Remember what we did with that last problem? It had a negative exponent. We went ahead and just flipped it over to start with. So you would have 2r to the 6th over 1 all to the 6th power. And then essentially, and we could write down a new property for this, but it kind of works like this problem did. What you do is handle these separately, as long as they're factors or divisors. Each one of them is going to feel the 6th power. So you're going to have 2 to the 6th, which basically comes from 1 times 6. You're going to have r to the 6 times 6. And then down here, you're going to have 1 to the 6th. Now, 1 to the 6th is 1 times 1. That's a lot of 1s multiplied together, and it just makes 1. And since you're dividing by 1, you can omit the bottom of this. The number of the denominator turns out to be 1. Dividing by 1 does not make a mathematical difference in life, okay? But up here, you may wish to go compute this. I think we did that in the previous video, and it came out to 64. So here's a very good way to write the final answer. I have no negative exponents. I evaluated this. I can see they asked me to do that here. So it looks good. Well, let me scroll it a little bit more. I think we're getting close to the end here. And now we're getting into this property that we talked about in the previous video, specifically this one right here. They want you to write the square root of 10 as some kind of a power of 10 that has a rational exponent. So remember, in the previous video, we had things like cube root of 125 is the same thing as 125 to the 1/3 power. Remember that? Here's one we didn't do in the previous problem, or previous video. The 4th root of 16, the positive 4th root, can be computed on a calculator as 16 to the 1/4 power. So now all you have to know is that for square roots, they never do, but they could put a little 2 there. That's the default root index. If you don't see a number there, it's just assumed to be a square root because they're very common. Well, that's the same thing as 10 to the 1/2 power. And that is the correct choice. 15 to the 1/3 power as a so-called radical. What do they want there? They want the cube root. That's pretty ugly symbol. Let's try that again. That's a little better. All right. 140 raised to the 1/8 power written as a radical. Okay, they want the 8th root of 140. And sometimes there's some simplifying that you can do with these. Trying to think, the best thing you could do with that would be to take a look at 2 to the 8th power and see if it divides into 140, and I don't think it comes even close, because 2 to the 8th power I think is already 256, so it's not going to work. All right, a little more scrolling, and then we'll be done. Find the indicated nth roots, the real nth roots of A. Okay, they're looking for a 4th root. There are 2 ways you could get your calculator to help you with this. You could, I believe your calculator's got a button that will do this. You might have to go to the, hit the second button first and look behind. You know how they have little green lettering behind the keys? But if that doesn't work for you, an easier way to do it is to go like this. And to get an exponent on a calculator, the key that gets used almost always is this little button right here. Anyway, the calculator would indicate that the answer is 3. But it turns out there's more than one way to do it. Is it true that 3 times 3 times 3 times 3 equals 81? Yes, it is, because that's 9, and that's 9. 9 times 9 is 81. So one of the roots is 3. But they seem to suggest that there's another root here. Well, there is. With an even number of factors like this, you could still land on a positive product like 81 if you had used all negatives. And I don't mean subtractions, I mean multiplications. Because what's negative 3 times negative 3? 9. Same here. And 9 times 9 is 81. The negatives just sort of cancel themselves out. But what that means is a fourth root of 81 is 3, but a fourth root of 81 is also negative 3. And those are the two real fourth roots of 81. Okay, now they want the fourth root of 256, and it's a slightly different question. When I write fourth root of 256, okay, I'm looking for the positive only solution to, well, one way to write it is like this. I want 4 things that multiply to make 256. There is a negative solution, but they didn't ask for it because the symbol in no way asks for the negative fourth root, real fourth root. If they wanted it, they would have gone like this. If they wanted both of them, they would have gone like this. Okay? So anyway, I'm thinking it's 4. Let's see if this will work. 4 times 4 is 16. And 16 times 16, check it out for yourself, that does make 256. There's other ways to know this. And you can do it on a calculator too. The answer is 4. And that concludes a review. I mean, I'm not saying this is the most complete or thorough review, but it does cover a lot of the things you need to know about powers, exponents, negative exponents, and rational exponents. Hope you enjoyed. I hope you learned a lot, and I hope everybody's happy and safe. See you later.